Hello, Fire Code Man, and hello, Pushy. Hello, Smart Coder. Welcome, all. A bad backpack. Yeah, it's not easy to get this backpack. You have to get top 3 in a contest. So we're gonna be doing the weekly contest 394, and I'll try to assume as little as I can, as little previous knowledge as I can. So let's see what we can do. So let's start with question 1. So as you can see in 1, hey Lucia, how's it going? As you can see, question 1 and question 2 are 2 parts of the same problem, but do you categorize this as an easy contest? Yeah, I would say that. I mean, compared with other contests. So the hard problem wasn't that hard, in my opinion. So, and you had people that finished everything very quickly. So, I wonder if that last one uses the Dijkstra's algorithm. Well, we'll see. We'll see. Let's not get ahead of ourselves. So, let's. This is question 1. So what I was saying is that it seems that like Q1 and Q2 are 2 parts of the same problem. So, but it turns out that they are not the same problem with different constraints as you could have thought. They're actually different problems. So let's do them in order. Because otherwise, you could, in a contest, if you think you're going to solve both of them, it's better to solve the one with the larger constraints, the harder one, and then use your solution for the easier one. But here, they are different. So count the number of special characters, 1. You are given a string word. A letter is called special if it appears both in lowercase and uppercase in word. Return the number of special letters in word. Okay. So notice that here we only care, we're only going to test if a letter occurs in the string. So the order and whether there are duplicate elements doesn't matter. So we can add this to a set, right? So we can create a set of the word, and then we can go over each letter. Hey, Meldin, thanks for the follow. Then we can go over each letter. And just check, right? So there is a way. I think there's a way of going over all the letters in Python. What was it? There's a string, Python string, alphabet. Yeah, I think there's this. So maybe we can use this. So for each lower case letter, we want to add 1 if the letter occurs in word, and also L upper is also in word, right? So this should be our solution. What but oh, and what is the matter here? All right. So easy peasy. Not a lot to talk about this one. So the order is linear in the length of the word, but only here, right? Only when we transform this into a set, because then this loop only goes over the characters, so it's the size of the alphabet, which is 26. And then this is O of 1, of course, to check if it's in the set. Yeah. Yeah, I guess instead of using a set, we could have used so we could have used a set of ASCII values, and then we go over the characters in Word, and we get the ASCII value of the character, and we add that one, or we make it true if that's, yeah. So here this is false, and so here which we can just say something like this. This would also work, but I guess the other one is simpler, so I would prefer the other one. So I'm gonna share my submissions. I always share them. I add them in the description of the YouTube video after I upload the video. Okay, so in this one, so a letter is called special if it appears both. So this is the same definition. It appears in lowercase and in uppercase, and every lowercase occurrence appears before the first uppercase occurrence of C. Return the number of special words. Okay, so this is a little different. So let's see. So here, so notice that again we're gonna process the each letter independently. So let's say that we have A. So let's say we're processing A. So it doesn't matter if we have other letters. So let's say we have an A here, an A here, and then we have a capital A, and another one, and another one, something like this. So notice that we only care. So this is asking us if all the lowercase are of A are to the left or of the uppercase. So notice that the only one that matters is this position here, the first one. Let's call this J, and the last position of the smallest one. So it doesn't matter where this is or this is. We only care about this one and this one, and the condition is whether I is less than J, right? This is, we find so in Python we can do this by searching. So to get the last, let's say this is S, so we can do S find, of the letter A, and this is going to give us this value here, the J. So this is going to be J, or -1 if there's no A there, and to get the last one of there's a rfind function which also returns so it's either going to return I or -1 if there are no occurrences. So let's do that. So again, we can use this to go over each lowercase letter, and then the upper, and then we want to find let's call it I was going to be the last one of the lowercase letter, and J is going to be the first one, so find of the uppercase letter. And so if I is less than J, this means that this is a special character and we count it. Okay. Oh, and we need to make sure, so we need to make sure that they are so let's say that if I is -1 or J is -1, then we continue. Right. Cool. Thumbs up. Yeah. Great. So yeah, there was not a lot to say about this one. I think it requires just a little logic and thinking. Well, the first observation is that you can process each letter independently, and then that it only matters these two positions, the first one of the uppercase and the last one of the lowercase, and then it's just straightforward after that. So let's move on to question 3. Minimum number of operations to satisfy conditions. You are given a 2D matrix grid of size m times n. In one operation, you can change the value of any cell to a non-negative number. You need to perform some operations such that each cell Q3 is a nice problem. Yeah. So grid of ij is equal to the cell below, if it exists, and different from the cell to its right. Return the minimum number of operations needed. Okay. And here we have a few examples. Here you don't have to do any operations. You don't have to change the color because you already have. So the columns are of each of one color, different colors. Yeah, but here, I don't know why they painted this the same color. It's a little confusing. and here you have 3 different colors in one column, and you have to paint them. You have to repaint at least 2. And okay, and the sizes are 1,000 by 1,000, and the colors are from 0 to 9 inclusive. Okay, so the first observation here is that so let's say that you have this grid, right? And here you have a column. So let's say, well, wait a minute. So yeah, and here you have let's say you have 5 rows. And so of course, if you paint this, let's consider the last one without loss of generality. Let's say we paint this red, right? So now this one has to be the same color as the one below. So this one should also be red. And the same for this one, the same for this one, and the same for this one. So that means that the columns, all the columns must be painted on the same color, right? So that means that so we can process the columns, right? So let's say this is 0, 1, 2, and C minus 1. So we can summarize the columns, right? So we can say, we can have a count that given some column and then some color, x. So x is going to be between 0 and 9. Is going to tell us how many, the number of cells painted with color X in column C, right? So we can create this, and now we got rid of the right, because once we have this, we're gonna have a table. We're gonna have a table that has here it's size C, where C is the number of columns. Hey, Saeed, thanks for the follow. So here we're gonna have a table that goes from the number of rows of this table is going to be C, the number of columns of the original matrix, and then this is going to be from 0 to 1 only. So we reduce the size of the input. One more follow to get, I think I got it right with this one. I got to 300, so thank you guys. That's great. So did you follow why we can transform? So we can transform the input to this thing here without losing any information. So we can forget about this now. We can forget about the original, and now we're dealing with the columns. So now how do we decide how to set the color of each column? Well, so maybe we don't have to be clever. Maybe we don't have to be greedy or anything. So so let's say that maybe we can do something with the p, with this kind of recursion. So let's say that we want to know the minimum operations starting from column I, and let's say that we remember the previous color, right? So this is going to give us the minimum operations. So remember that the operations are changing one cell to a different color. Minimum operations to repaint starting from column I, where the previous call was painted prev color. Okay, so once we have that, notice that, well, if we got to the end, so if I is greater than or equal to the number of columns, then we don't need to do any more operations, right? So we return 0, right? But otherwise, well, we don't have to be clever. We can just try each color, right? So for color X in range so we have 10 colors. If X is different than the previous color, right? We don't want to repeat. Then what is going to be, so if we decide to color the current column of color X, then we're going to have the sum of the, no, wait. So here we have to repaint. So we have C columns in total, right? But we want to subtract the cells from column I that are already painted of color X, right? So we subtract these ones we don't have to repaint, right? So this is the cost of painting column I. We could have called this instead of I, call C for column, but it's okay. Maybe we'll change it. Okay, so this is the cost, the number of operations that we have to do to paint column I of color X. And we can do this because it's not the same as the previous color. Okay, and now we have to also add the mean cost of the remaining of the next columns, right? So here, this is I plus 1, and now the prev is going to be X. Okay, and we want to take the minimum of this, of the whole thing. This is going to be our answer, right? We want the minimum cost choosing each color. And since you notice, so this is, so we found a recursion that solves our problem. So notice that there are So I can have at most 1,000 values, and Preb can have at most 10 values, right? So this is going to be 10 to the 4 subproblems. Subproblems, right? So that's not a lot. And then we have 10 transitions. So in total, we're gonna have 10 to the 5 iterations, operations. Okay. So that's within what we can do in LeetCode. So if we cache this function so that we do not recompute values that we have, we don't solve sub problems that we solved before, then this is going to be fast enough. So now we can just do, we can just write, I mean, it's pretty much the same code. So this is the length of the grid. So let's compute this, which is going to be of the size of the, so this is how we transform our input, right? So here we want to count for the column, and for this color we want to add 1, right? So this is what we defined before. And now let's have our memorize function, which is the minimum operations. Let's call it C, and let's call this prev or prep. Okay, and so if C is equal to the total, then we're done. We don't have to repaint anything else. We don't need any more operations. And here we want the current color from all the possible colors, if the current is different than the previous one. And here again we have yes, this was not C here. This is this should be R, right? Because those are how many cells we have in the current column. So we have R cells, but we want to subtract the ones that are already painted in the current color. So this is the number of operations that we need to paint the current column of call cur, and then we add the minimum operations for the rest, and here now the previous is going to be cur, and we want the minimum of this. This cannot be empty, and here we return and let's say that the initial color is -1, the previous color to the first one is -1, so that we don't care about the color. And this works of course. So notice that we can also do this in we can do this bottom up, right? Which you'll notice that it's pretty straightforward once you have the recurrence. So here we're gonna have a min op array. Okay, that, so notice that you can save memory because for every sub problem we're only looking at C. So for C we're looking at a sub problem with C+1, right? So we can do them from the largest column to the and we only need the previous values, right? So we can do, let's call this, no, that's okay, it's min op, and we go from, yeah, let's call this C, from the last column to the first one. And now we pretty much need to do we need to, well, we also need to know which the previous value is. Okay. And now for the current, so here we have the new min op, and so the new min op of prev is going to be this. Notice that it's pretty mechanical how you go from top down to bottom up. And here yes, the only problem here is that we don't have a -1, but I think that is if we so here we have to update the min op as the new min op. But the only problem, how do we deal with this? I think it will work if we just get the, is that your solution, smart coder? So I guess if we do this, it should work. Yes. But I guess another trick would have been to add another color, like a special color. But yeah, I left, right? This, I don't want to have that. I don't need that anymore. Oh, you got an ad? Can I disable ads? Okay, so no, I ask whether that's your solution to this problem. Is there anything special that you want to show? So I'm showing the top down and the bottom up solutions. Okay, so I'll share my submissions like I said on the YouTube video. So let's move on to the last one. Find edges in shortest paths So did you follow how to do the previous one with bottom-up DP? Okay, so find edges in shortest paths. So we're given an undirected weighted graph of n nodes. Okay, so this is the usual way in which you get an undirected weighted graph. And consider all shortest paths from node 0 to node n minus 1. You need to find a Boolean array answer where answer of I is true if the edge is part of at least one shortest path. Otherwise, answer of I is false. Okay, the graph may not be connected. Okay. So, well, here, whenever you have to find shortest paths in an unweighted, in a non-directed, well, in a weighted graph, without negative weight edges, of course, then you can use Dijkstra's algorithm. So that should be the first intuition when you get this kind of problem. But here the catch is that we have to consider all shortest paths. So usually Dijkstra finds one shortest path, but could be more than one, right? So we have to think about how we can modify Dijkstra so that we can find the edges of all the shortest paths. So first of all, notice that the number of shortest paths can be exponential, right? So notice that if you have you have this graph, right? You have a node here, and then you have two nodes, and then you go back to one node, or even something like this. You have this node, yeah, without this one, I guess. And then here you have this too. And let's say that all the edges are weight 1. Right? So every time you move from one level to the next, but you have two options, right? You can go to here, you can go to this one or this one, and then you have two options. You can go to this one, and so on. So here, if you have n nodes, you're going to have the number of shortest paths is going to be something like this, right? And let's say that n is even. So that's just for you to understand that we're not going to go over all the shortest paths because there are too many. But it's not the same to go over all the edges belonging to at least one shortest path. So like I said, I'm not going to assume so you must have heard you must have studied Dijkstra before to understand this, but I'm gonna do a little review. So let's say that you have this node 0. Here we have node 1 and 2, and node 3, 4, and then this, let's say that we have the last one here. Okay, yeah, let me fix this. So let's say that this edge this is 1, this is 5, this is 3, this is 2, 1, 1, 2, 5, this is 2, and this is 1. Okay, so here we have our graph, and we want to go from 0 to 5, right? So we have, so here n exists, and we want to go from 0 to n minus 1, which is 5 in this case. And so remember how you do Dijkstra, right? So initially, we set all the distances. So the source here is 0, so the distance to 0 is 0. But the distance initially is going to be infinity to each other edge, to each other node, sorry. And so now we go, so we make this node final, right? So now this node is final, and this is the shortest distance, right? And so now we update all the adjacent nodes. So here 1 is adjacent, so now we can get to 1 by the distance that we got to 0 plus 1, so we can get with distance 1. And here we can get to 2 with distance 5. So remember that in order to reconstruct the path, you can have a predecessor. You can remember how you got to the current node. So here we got from 1. So far we gotten to 1 from 0. So let's say the predecessor is 0, right? And the predecessor so far for 2, it's also 0. So now we want to process the next next closest node that we haven't processed yet, which this one has distance 1, so it's the smallest one, right? So we now set this as done, and we go to the all the adjacents. So here to 3 we can get from here, so we can get from distance 3, and now the predecessor of 3 is going to be 1. We can get to 4 with distance 2, and now the predecessor of 4 is again 1. And here we already have distance 5 to this node, but now we can get from this way and get a distance of 4, right? So we update it, and now notice that now we need to also cancel. We need to remove this as the predecessor, because now we got from 1 with a shorter distance. Okay, so now we updated all the adjacents, and now we get the closest one. So this is 3, this is 2, right? So this is the next one. So we set this as done, and we go over here. So notice, now this is the important part here. So notice that now this is 3 is an adjacent node of 4, and we got to 3 via this node with distance 3, but we already got to 3 from a different path from 1 with distance 3. So we don't update the distance, but now we add 4 as a predecessor. So now our predecessor our predecessors are not going to be only one. Usually when you do Dijkstra, you only have one predecessor, and that's enough to be a shortest path. But now we're going to have all the nodes that get to this one, to the current one, with the shortest distance, right? So that's why we have lists now. And so finally, once we, so here this is 3, and here we got to 5 with distance, what, 4? So the predecessor of 5 is going to be 4, right? And here we got this way, so this is going to be longer, so we don't update anything. Okay, so now the next one is going to be this one. And so now we can get to 5 again. We got to 5 with distance 4. So again, we don't update this, but we add 3 as another predecessor, right? So let's say that we've done. So here we finally finish this node, right? And we've done, we did Dijkstra from all the nodes. And so now we want to know all the nodes. Okay. So now we're going to start backwards, right? So this is the end of our path, of our shortest, of all the shortest paths, right? And we look into the predecessors, so we can get here from 4 and from 3. So now we add these edges. These edges are going to be part of the shortest paths, right? Because of what we said, we can get from 4 or for 3. And now we can do this recursively, right? We can now find the shortest paths from 4, for example. And what was the predecessor of 4? It was 1. So now this one is in a shortest path, right? And then we go to 3, and we say we got from 1 or from 4, right? So this is part of a shortest path. This is part of a shortest path. And finally here, so we're doing a traversal of this, which is it's another graph, right? And we're doing a traversal starting from this node. Okay. So why am I saying that it is another graph? Because we're only having some of the nodes, right? For example, here. So this edge is not part of this subgraph because we didn't get to 1 with the shortest paths from here, only from 0, right? So that's, we can do a BFS or a DFS traversal starting from the end, and we mark all the edges this way. Okay, so the code is going to be pretty standard, right? So we create. So notice that we're going to need the index of an edge, because we have to return a list of the size of the edges, the number of edges, and each edge has an index in that list. So we're gonna have a let's save a dictionary, which is going to give us from an edge its index. Okay, so here, and we also want to have an adjacency list in order to do the Dijkstra. And so we're gonna have UBW in, let's enumerate the edges so that we have the index corresponding to the edge. And here, so here we want to append the edge from U to B and from B to U with the weight, and we want the index of UB equal to the index of BU. It doesn't matter how we which side. This is undirected, and this is going to be I. Okay. So now we can index the edges. That's going to be useful for giving the answer. So now this is the standard Dijkstra, right? We set all this is what we did before. We set all the distances to infinity except for the source, and then we create a heap with distance 0 to node 0, and while the queue is not empty, we have the distance to U and U. We pop the heap, and if distance to U is not the best distance, then we continue. We want to process nodes only once, and then we go over the adjacent nodes, right? And yeah, remember that we also wanted to have the predecessor, and we want this to be a list for each node. And so here we want to see if the distance to B is greater than the distance to U plus 1 plus W, right? So if we found a shorter distance, then we update it, right? So we want distance to be the new distance, the shorter distance, and we want the predecessors of B to be only U, right? Because this is better than what we had before, and we want to push to the heap this new distance. But also remember that if we tie, if we found another path, so we found another path to the same node with the shortest distance, so if this B is equal to this U plus W, then in that case we added to the predecessors of B, right? We don't need to push it because it should be already there. We already reached node B with this distance, right? And so now we're done. We've run the Dijkstra. We have the predecessors, and now we can do DFS or BFS. I'm gonna do BFS, breadth first search, because in Python is faster to you want to avoid sometimes recursion, which is a little bit slow. So let's do. So we want to keep track of the nodes that we've seen. So, and we're gonna start from n-1, and we want to queue, and we want to have the result, which is going to be, let's say that by default they are all they are not in a shortest path at the beginning initially, and this is going to be the length of the edges. Okay, and now we do standard BFS. Okay, but here, well, this is not, sorry, this is not, here we want the predecessors of U. And here we are considering an edge, so this edge should be from U to B. Now it's part of a shortest path. Okay, so this should be it. And it passes the examples. And accepted. Cool. So yes, here I'm gonna share my submission. But again, remember, nice, thank you. Remember that you can do the you can find all of my submissions in the YouTube video once I uploaded, once I exported the bot from Twitch to YouTube. So yes, I think I went through the whole thing here pretty in a pretty detailed, in a lot of detail. So if you have any questions, let me know, or if it's clear. So yes, like I said at the beginning, I think this wasn't the hardest contest. So I think someone that had studied Dijkstra and DP with basic knowledge of Dijkstra and DP could solve the 4 of the problems, 4 out of 4. So yeah, that's all I got. So thank you for watching, and see you on the next one. Bye bye.